Hello, good day everyone. Okay, so today we will continue discussing stresses and beams. Okay, so this time we'll talk about shear stress. Okay, so last sessions in this topic stresses and beams we talk about or we discuss about uh, bending stresses. Okay, when we say bending stresses, it was caused by bending moment. Okay. And when we say shear stress, it is caused by shear forces. Okay. So the general formula for in computing shear stress is like this. Okay. So shear stress is usually referred to as tau. Okay. In Greek letters. Okay. And it is equivalent to VQ over IB. Okay? So here, V is your shear force. Q is your first moment of area. I is your moment of inertia. And B is your base width. Okay. So, looking upon this form, this is actually the general formula. Okay. So, you might ask, what is the difference between this formula and this formula? Okay. So, you might be bewildered. Okay. So, maybe in the past, you have heard of this formula in which if you have a cross-sectional area and then it is experiencing a shear force, you can compute the shear stress by this formula. Okay. So, what's the difference between this formula and this formula? Okay. So, this formula is more of an average shear stress. Okay. So, in other words, okay, this formula is more of an average shear stress. Okay. So, it does not necessarily reflect the shear distribution in your cross-sectional area. Okay. So, in this case, okay, so in the past, maybe in your basic physics, okay, so maybe in your high school physics or in a previous, okay, in our first chapter in mechanics of deformable bodies, we say that your average shear stress is the shear force over the area. So it is more of average shear stress. While in fact, so this is okay, or in fact, in actual situation, okay, we know that shear stress is a stress that, okay, parallel, okay, and parallel to the area, not perpendicular, just unlike axial stress. Its stress distribution is more likely like this. Okay. In which at the ends it usually had a zero shear stress. Okay? At the extreme and extreme top and extreme bottom, it usually experiencing zero shear stress. And then it will curvilinearly increase up to the neutral axis. So at the neutral axis, it usually experiences the largest shear stress. Okay. Okay. So So let us now discuss how do we apply this formula. Okay? So what is the first moment of area and what is the base width? Okay? So in this case, your base width, since it is a rectangular in cross section, so it has a base width of constant b. But not all the time that the base width is constant. Okay? For instance, example, we have a I-beam. Okay? So when we refer to the shear stress, somewhere at the flange, okay, or somewhere at this portion, okay, in this portion of your I-beam, in which the width is obviously wide, b, so you use this b. Okay, so when we say what is the b in this portion, when we talk about what is the maximum shear stress and what is the shear stress at this point, okay, so you use this b. Okay, so it depends. There were types of shapes, okay, in which the base of your cross-sectional area is not constant. So there might be a time in which your b, there might be a portion of your cross-sectional area in which the b is wider, and there might be a portion of that cross-sectional area in which the b is relatively smaller. Okay, so for this case, more likely that the shape of your stress diagram would be like this. Okay, okay, so it would be still be the same. Okay, so at this portion it would be like this. Okay, in which it is still that at the top, at the sides it would be at at far top it would be 0, and at the far bottom it would be still 0, and somewhere at the neutral axis it will experience the rho max. Okay, so it's still the same. Okay, so it is quite parabolic in shape. Okay, in contrast with your um, bending stress. Okay, your bending stress will shape like this. Okay, this is your bending stress, in which maybe at the top it could be, depending on the direction of your force, it's either um, compression at the top and tension at the bottom, or tension at the top and compression at the bottom. Okay, so if you want to review it, okay, so I have videos in this channel in which explains the shape of bending stress diagram. Okay, so this is shear stress diagram. Okay, so it is parabolic in shapes. Okay, and it has 0 value of your shear at the top and at the bottom. Okay, and then it experiences the maximum shear stress somewhere at the neutral axis. Okay, and then this neutral axis is where located your center of gravity. Okay, so to where your center of gravity is located, you'll probably in that portion you can compute, okay, your your maximum shear. Okay, especially um, for these common sections such as rectangular beam, and I-beams. Okay? So here, okay, so I will uh, so maybe I will try discussing this Q. Okay? This formula. We're gonna try to elaborate this formula and how we are going to compute your shear stresses, okay, using this formula. Okay, so we'll have an example. Okay, so have another board. Okay, okay, okay. Okay, so let's consider this drawing, okay, this figure, okay. So actually, your Q is equivalent to the area multiplied by the y bar, in which the y bar is the distance from your neutral axis. Okay, so when we say neutral axis, it is the portion of your cross-sectional area where you can found your center of gravity or your centroid. And then from that neutral axis, uh, um, you measure, okay, you draw a line, a vertical line from that neutral axis to the centroid of this area, okay, in which the bottommost part of that area corresponds to your shear. Okay, so if you want to find, okay, this shear at this point, okay, at this location, okay, at this point of your drawing, okay, so let us say that you want to try finding um, the value of your shear stress 100 mm from the top. Okay, so since this is a rectangle, your neutral axis is located 250 mm from the top, or h over 2. Since this is the B and this your h is equivalent to 500 mm, and since it is your rectangular beam is actually it's a symmetrical shape, so therefore the location of your your centroid is equivalent to h over 2. So that is how you compute your Q, or your first moment of area. Okay, so from this figure, we'll try to compute your shear stress located 100 mm from the top of your beam. Okay, so we'll try. So I will just get calculator. So we can now compute your first moment of area. Okay? So please take note, okay? So your y bar is equivalent to 200 h over 2 minus 100 over 2. Okay? So your h over 2 is 250. Okay? H over 2 is 250 minus 50. Okay? So we can compute your y bar as 200 mm. So if that is the case, we can already compute your shear stress. Okay. No. We compute first our first moment of area. So Q is equivalent to A. Okay. When we say area, we're talking about the area at the top. Okay, at the top of that 100 mm. Okay, since we are trying to find the value of our shear stress, so this shear stress located 100 mm from the top of your beam, or from the top of the cross section area of your beam. So we'll find this area. Okay, so this area is equivalent to, okay, so we'll compute first the area. So area is equivalent to 100 mm multiplied by the base, which is 250 mm. So you will get 25,000 mm squared. Okay, so we can already compute your first moment of area, which is equivalent to A plus y bar. So therefore, 25,000 mm squared times 200. Okay, so we'll get 5 million mm cube. Okay, so we'll try. Okay, so we'll try solving it in this portion. Okay. So we have, okay, so we compute then first, okay, we compute after computing Q, we compute the moment of inertia. So the moment of inertia for a rectangle is equivalent to BH cube over 12. Okay, so please remember that the moment of inertia we are using in computation of shear stress is the IY, I sub y, not I sub x. Okay, also for bending moment of inertia we use I sub y. Okay, so our B is 250 and our H is 500. So we'll compute 250 to the power times 500 to the power of 3 divide 12. So we get 2,006,166 mm to the power of 4. Okay, and then from this drawing, okay, from this figure, we know that B is 250. Since it is a rectangle, undoubtedly at this portion, it has constant B throughout, since it is rectangular in shape. So your B is 250 mm. So okay. So one thing I forgot to put a value of shear. Okay, so let us say our shear is 100 kilonewton. Okay? So, your 100 kilonewton, okay, so let us say, so we need to convert this into Newton, okay, so that we will have a uniform units, okay, so 100,000 Newton, okay. So we can now compute our shear stress at that portion. So therefore, V times, okay, the V is 100,000 Newton times Q, which is 5 million mm to the power of 3. We have DI, which is this 2,604,166, 2,604,166,667 mm to the power of 4 multiplied by B, which is 250 mm. So we can compute our shear stress, okay, at that location. Okay, so therefore, okay, so if my computations are correct, so we get 0.768 Newton per mm squared, or 0.768 megapascals. Okay. Or maybe, okay, so this will be our answer. Okay, so our answer is correct. Okay.